Good evening and welcome. It's 5 o'clock, so I propose we can start with this Inspire webinar, and it will be a very interesting webinar and hosted or organized by TSE System, which is one of the partners of the Inspire project. My name is Professor Peter Jan Guns. I'm professor at the University of Antwerp, and I'm also a coordinator of the Inspire project. For those who don't know the Inspire project, it's a European training network, so it's funded by the European Commission, and it has two major aims. One is to train a new generation of young scientists, and we do that, for instance, also by organizing webinars, but we are also having 15 students or early stage researchers that perform their PhD research. And by doing that, we come to the second aim of our project. It's improving cardiovascular safety assessment. And as part of that, TSE Systems is part of the Inspire training network. And so together with TSE Systems, we try to explore technology to improve safety assessment. And that's why we come to the topic of today. And so today we will have a webinar about telemetry in group-housed rodents, which is quite complex, but it's really enabled by technology. And today we have a team of experts of TSE, which can share their view and also share some tips and tricks how to make this happen. With this, and without further ado, I want to pass the word to Holger Russich, who is a scientific director at TSE, and which will also further moderate the session or the webinar today. So, Holger, the floor is yours.
Thanks a lot for the kind introduction, Peter Jan. Thanks to all of you being here this afternoon with us. So I will try to give you a short overview about what we planned, but before I go into that issue, I would like to share some technical issues with you. So first of all, please unmute all yourself so that we have not many disturbances during the webinar. And the second, we will run a very short Q&A session after each of the talks, and this will be done via the Q&A button in your menu light. So that please use this button, type in your question, and we will try to answer the question quickly after the talks. And at the end of the webinar, let's say in about 2 or 3 days, you will get a handout of all the questions and the answer in a subsequent email. So as I said, I will give a very short introduction into TSE, what we are doing, which is followed then by a talk by Irina, which is from Kent Scientific, and we'll talk about how to do in a really 3R-oriented way anesthesia today, which is followed by a talk from René Remy, which is really an expert in surgery methods and which you need to implant telemetry. And subsequently, we will have a talk by Bob Brockway, which will tell us about how to do telemetry in group-housed animals today. So I think with this kind of introduction, I will quickly jump into what TSE is doing. And for those of you which are not familiar with the company, so we are pretty long in the market. We are a German company with our headquarters in Berlin. And what we are doing is basically we are providing research equipment in 4 main areas of research. The first area which we are focusing is behavioral. That means all the cognitive assessment as well as kinematic analysis of animals, which you need to characterize animal model of different diseases. The second part of our interest is the main focus for today will be the stellar telemetry, which can be used to monitor 24/7 biopotentials such as EEG or pressure such as blood pressure. Probably our biggest area of research which we are supporting is the metabolic area, where we have an automated PhenoMaster system in the market, which allow you to do indirect telemetry and monitor every changes which have an impact on energy expenditure, such as food intake, liquid intake, or body weight changes, as well as locomotor activity and others. And last but not least, we also are active in the area of inhalation, where we can produce all kinds of different aerosols, bring them to an animal using nose-only or whole-body exposure systems, and then take care also for the rest. And with this short introduction of TSE systems as such, I will hand over the floor to Irina, which is the global sales manager and scientific development manager for Ken Scientific, and they are quite famous in the area of low flow vaporizer, which you can use easily for anesthesia today. And with this kind of introduction, Irina, thanks for joining us here today.
Thank you, Holger. Thank you, guys. I'm going to share my screen with you. Can everyone see that?
Yes, we can
Okay,
see.
great. So today, thank you everyone for joining us. I'm going to talk a little bit about the physiological monitoring and about the anesthesia systems that we provide for the preclinical drug discovery market today. Most of you guys who do surgeries or any type of monitoring are familiar with this traditional anesthesia system. It was originally designed to be used with larger animals like cows, pigs, dogs, and so on and so forth, and later on adapted to be used with smaller animals under 1 kilo. So even though accessories such as face masks and induction chambers were adapted to be used with smaller animals, the flow rates of the traditional vaporizer was never really brought down. So the small animal like a mouse that weighs 30 grams or even a rat that weighs 300-400 grams was given a large flow rate of isoflurane, and therefore there was a lot of extra vapor waste and exposure to both animal and the users. So about 10 years ago, we came up with this concept of low flow electronic vaporizer. The one you see on the right hand side is called the SomnoSuite, and about 2 years ago we came up with the one you see on the left hand side called the SomnoFlo. The concept of these was to deliver exactly what the animal needs. So if you have a look at the SomnoFlo anesthesia system, it's delivering based on the weight. It uses room air versus compressed gas. It does not require calibration because electronic vaporizer versus the traditional vaporizer. So what makes the SomnoSuite unique system is, as I mentioned, precise delivery of anesthesia, solid state electronic design. As I also mentioned, no annual recertification is required, and room air versus compressed gas. Low flow rates allow you to deliver to the animal exactly what they need and not to over deliver, which also means that you have less waste anesthesia gas exposure, and no one should be smelling isoflurane basically. The system is compatible with both isoflurane and sevoflurane, and the flow rates can go as low as 50 mils per minute and as high as 1 liter per minute. So as you can see on this picture, it's a very easy to use integrated screen. Isoflurane goes into the syringe. You can attach the syringe to the bottle and draw the isoflurane in with either 5 or 10 ml syringe. So again, with this, you can deliver to the 30-gram mouse exactly what the animal needs and not expose it to extra isoflurane. Here's how to use it. You take the syringe, fill it with isoflurane, place it on a syringe block, and then as you can see the black block in the middle of the unit, that is your vaporizer block. In comparison to the traditional vaporizer block, it's a lot smaller, and again, it's electronic, so it does not require annual calibration. This particular unit, the SomnoSuite, is called that way is because it can house other modules, such as the right temp, which is homeothermic warming, pulse oximeter, heart rate and pulse oximetry monitoring. It can also house the ventilator and the CapnoScan and tidal CO2 monitoring. So the last two modules, the ventilator and the CapnoScan, kind of have to go together. So in order to measure CO2 properly, you have to intubate and ventilate the animal. So all of these modules are included in the body of the SomnoSuite. Here's a basic chart. This is a completely closed up system. So you have the inspiratory and expiratory ports that are labeled blue and red, and they split, and one goes to the induction chamber and the other one goes to the animal. Whether the animal is in a face mask or stereotaxic system or the ventilator. The clips allow you to deliver the isoflurane to either induction chamber or to the animal. In the back of the system, you see 3 airs. The blue one allows for the room air. The green one allows for the compressed gas if the compressed gas is desired to be used. And the red one is for the waste gas anesthesia canister. Only canister is required for the waste gas because of the low flow. No active scavenging is required with either SomnoSuite or the SomnoFlo systems. So about 2 years ago, we came up with yet another, as I mentioned, low flow vaporizer, SomnoFlo. And the SomnoFlo is different from the SomnoSuite as it draws isoflurane directly from the bottle. So as you can see here, the bottle is attached right to the unit, and therefore there's no need for the syringes anymore. All the other options, as far as the low flow vaporizer, are still the same. The low flow rates, the no need for compressed gas, and no need for calibration. These are the features of the SomnoFlo. Again, low flow delivery. This unit is not going to house any other modules. It's a strictly low flow vaporizer. So it is important to mention that with any vapor anesthesia or any other anesthesia, the warming is needed. SomnoSuite had a warming pad called right temp. SomnoFlo does not, but one should always practice safe experiments and use the warming. If you can have a look at this chart here, SomnoFlo is the same way connected so that the tubing goes to either induction chamber or the animal, whether it is on a face mask, again, stereotaxic system, or the ventilator. And then the charcoal canister is incorporated to draw the waste gas. Here's another example for you guys. You can use 2 animals on, on the SomnoSuite or SomnoFlo. And the only measure to be aware of here is that the total weight should be up to 1,000 grams. The system can only accommodate animals up to 1,000 grams. So as long as the mice and rats total are under 1,000 grams, they can be used 2 animals at one time. Here's an example where the animal is connected to the ventilator. This is our ventilator called Rovent, but one can use their own ventilator. It could be incorporated into the setup. And of course, in this case, you're using ventilator, you need to intubate the animal. Here's another setup example with the stereotaxic frame. We provide the stereotaxic frame attachments for systems like stolting and cough. And the tubing is included in all of the SomnoSuite and SomnoFlo kits. We do not provide the actual nose piece attachment that either stolting or cough-like systems have. Now, I wanted to talk a little bit about the physiological monitoring. As I mentioned, warming is critical for any type of surgery or physiological monitoring with the anesthesia. And so we provide what's called the PhysioSuite with the right temp here. What you don't see is there is no warming pad in the picture, but I'll scroll through a few more slides and you will see the warming pad. This unit also has a mouse stat and a CapnoScan. The mouse stat is for the heart rate and pulse oximetry, and that is using the paw sensor. The paw sensor is placed on the paw of the mouse or rat. This here, you see the right temp monitoring system with the pad. So the pad is attached directly to the face of the unit. And then the other 2 spots are for the probes. It's far infrared warming, so it warms directly through the tissue. The rectal probes are flexible for either rats or mice or any other small animal such as hamster, or chinchilla, or even the marmoset. You can pre-program the unit to reach appropriate temperature, and if the temperature goes up or down, the unit will automatically correct the temperature and bring it to the set temperature. You can also connect it to the computer for the automatic feedback control and record the measurements as well. This is an example of the mouse stat module of the PhysioSuite with the pulse oximetry sensors. There's also an option for the respiratory rate monitoring, again with the automatic feedback. CapnoScan is actually the unit is the side stream capnography. So it attaches to the back of the PhysioSuite, and then you intubate and ventilate your animal, and then insert the needle into the expiratory port of the trachea tube to collect the CO2 measurements. This is our Rovent automatic ventilator that can be used as a standalone unit with either SomnoSuite or SomnoFlo or the traditional vaporizer. It has a couple of options. There's a Rovent Junior and then the Rovent Advanced unit that allows you for additional option like inspiratory and expiratory cold, built-in PEEP option. All you need to do here also is just set the animal weight, and the unit will adjust all the other parameters. And this is another form of physiological monitoring called non-invasive blood pressure. CODA monitor is designed to be used for one animal here. We also have the high throughput system. In the discussion of the CODA monitor, there are 6 parameters that are measured and recorded: systolic, diastolic, mean arterial, tail flow, tail volume, and the heart rate. This particular model can be used without the software for one animal, but also can be used with the software. This particular unit can be used for up to 8 animals. And the infrared warming pad platforms are what you see there for 4 animals each, controlled by the software only for the high throughput system. And we also provide the non-contact infrared thermometer that allows you to monitor and measure temperature of the animal via tail. So in short, far infrared warming products that we provide that could be used with our either vaporizers or any other are simple temperature target options. All are homeostatic options. All are including infrared warming pads, and they're very small, basically like a handheld device. From left to right, you see here 3 possible options, from the simplest one that you can measure the temperature to the more advanced one on the very right hand side, SomnoSuite Right Temp. For the surgical purposes, we do provide the surgery suite, which is the warming platform with the surgery board, with the accessories such as lights and warming and also magnification. Stainless steel platform around it allows you to use magnets and the positioners. So this is also can be attached to the vaporizers. And that's about all today. And if you have any questions, I'm available to answer them now with Holger, or you can email me. Thank you, guys.
Thank you very much, Irina, for sharing this interesting information about all the equipment useful for doing surgery. So obviously your talk was quite clear. There's no question in the chat. So I will hand over, due to time reason, to René Remy, which is, can you see my screen now?
Yes, I can see you.
Yeah. Which is really an expert in terms of lab animal science and a lot of experience with surgery skills in the context of 3R and optimizing surgery for telemetry implants. I'm really happy to have him here. And René Remy did a PhD in pharmacology, working on neurotransmission, and then co-founded the Microsurgical Developments Foundation, which is he still now a host of that. And as I said, he has over 45 years experience in lab animal science and in doing surgery, and is one of the guys who is doing perfect training for telemetry implant surgery, and I'm really looking forward on his presentation about how to do optimal surgery to ensure basically to have high quality telemetry data. Thanks a lot for joining us, René. The floor is yours.
Thank you. I will share my screen, and if everything is okay, you have a shared screen now. Thank you, Holger. Yeah, we just heard a lot about the anesthesia. Of course, there's no surgery without anesthesia. And we also talked, or you heard a talk from Irina about keeping animals warm, and I will come back to that later. Okay, when we talk about surgery, what in fact is the problem? Surgery is often done by people who are not trained to do surgery. And that very often leads to what we call animal-consuming autodidactism. The use of living animals, technical failure, high number of animals are used during the training phase. People do not really know how to handle tissue, and that often leads to what we call meatball surgery. And that, of course, leads to unnecessary suffering and probably to unreliable results. Next to that, when people come here at our training center, their starting experiences are very, very different. And some of them have a lot of years of experience, but they also have some bad habits. Fortunately, there is quite a bit of legislation and guidelines at the moment. It started in '86 with the 609 guideline, and then around 2000, the International Conference on Harmonization issued the S7AMB guidelines for safety pharmacology. And there, amongst other things, they talk about the use of radiotelemetry. 201063 is the guideline we are working with at the moment. What are the pitfalls in training? Normally, information is lost along the line. And when a student is trained by an expert, in some time, the student will become the teacher of another student, and that student in his turn will become a teacher of another student. And this is what we call the Chinese whisper. And at the end of the line, the story is completely changed. Next to that, you very often take over the mistakes of your teacher. That's not your fault, but your teacher's fault. But anyway, probably not so good for the animal. Some people that have some experience already start being a teacher, and this is the credo: see one, do one, and teach one. And that is not what we should do in laboratory animal science. Next to that, when you have an experience in surgery and you have done it for quite some times and you have bad habits, it is really difficult to get rid of these bad habits. And during stressful events, what we very often see is that the system goes on autopilot and you still go to your bad habits again instead of the good ones. Having said that, I take you back in time to the years before 1846, where there was no anesthesia and surgery was in fact done at a very high speed, with one of the champions there, Professor Robert Liston, who could do a lower leg amputation in 28 seconds. And that is really quick, I can tell you. At the end of 1800, the modern surgery was born, and time was no longer the most important factor. William Stewart Halstead started with the invasion of the body, and it did some approaches of the gallbladder and the thyroid gland. Of course, next to the normal Hippocratic approach that you should not do harm to your patient, Halstead took this principle one step further and said you should not harm the tissue of your patient. And that was a step in the good direction, and this is what today is called good surgical practice. It's in fact a set of interrelated principles that is about tissue handling, about tissue exposure, about hemostasis, and about asepsis. And we will discuss these four interrelated principles in the next couple of slides. Minimal surgical trauma is important, and therefore tissue handling is really important. What you should remember is that every time you pick up tissue with your instruments, you kill cells. And what you should try to do is kill as few cells as possible. And therefore you must be goal-oriented in your approach. And next to that, remember that sharp dissection most of the time is less traumatic compared to blunt dissection, but it is more dangerous. That leads us to a saying that a rule of thumb that sharp when can and blunt when must. That's a good thing to remember in surgery. Yeah, goal-oriented. Here you see a target of an archer, and I have a lot of archers in my family, and this is my youngest son. Really, goal orientation is the key to success. It increases the speed and it decreases the amount of trash that you make. I also want to draw your attention to a paper that was published in 2000 called The Thin Blue Line by D.M. Cooper and colleagues. And in that paper, they say in so many words that the contribution of surgical technique to the prevention of post-procedural infections is probably equal to that of aseptic technique. And I wholeheartedly support this opinion. The next principle is exposure. Make sure that your view is unobstructed and that you have proper illumination and that you can have access to all the parts you need. Make your wound in the beginning sufficient in size. Don't do keyhole surgery. That will come. When you get better and better in the surgeries, you will see that your wound size will decrease gradually. Don't worry, by the way, about wound healing. In rodents, it's extremely fast, and it is more affected by proper approximation of wound edges than it is affected by the size. Since we talk here about implantation of radiotelemetry devices, it is important for you to know that asepsis is really crucial. First of all, you should have a meticulously sterile technique. But second, and this is absolutely as important, make life miserable for bacteria. So take away their food by removing dead tissue, by removing blood and serum residues. What you should remember is that in the presence of a foreign body, there is a 7 times higher chance on a post-procedural infection. Irina already mentioned the fact that you should keep your animal in the physiological range when it comes to its body temperature, and that is very, very important. Avoid hypothermia, because hypothermia itself can double the chance of a post-procedural infection. Next to that, remember that time is also a form of trauma. We call it the 3 T's: time, trauma, and trash. Of course, trash is the reduction of the aseptic technique. Trash reduction is aseptic technique, in fact. But when you do take a long time to do your surgery, that can be impaired local blood supply, prolonged anesthesia times resulting in hypoxia, and that all is very bad for your animal when it comes to post-procedural infections. The last principle is hemostasis, and this strongly depends on your animal, of course, but a lot of people today work with mice, and we should remember that a mouse has only a teaspoonful of blood, some 2 mils circulating, and you cannot afford to spill more than 10–15% of that, otherwise you have a hypovolemic animal. The first thing that you should do when you have a small bleeder, according to Hitchhiker's Guide to the Galaxy, is don't panic. Because if you panic, you're probably doing the wrong things. And the thing you should do is put your finger on the bleeding spot and apply light pressure. If you do that, most bleedings will stop after a minute or 2. But there are also other ways to stop bleeding. And one of them is coagulation. Very popular is the bipolar coagulator in microsurgery, where a high frequency current is running between the legs of a forceps, locally warming up the tissue to 60–70 degrees centigrade, and thus closing a blood vessel. A cauter can also be used, but the cauter gets very, very hot and spreads its heat a bit more in the tissue, so you will have a larger area that is affected. Of course, you can use a tie to block the bloodstream ligation, and we have our hemostatic sponges that most of the time contain collagen fibers, but also the new modern ones contain fibrin and thrombin, and they really work very well. Coming back to safety pharmacology and the species we use there. Very popular species when it comes to rodents are guinea pigs, rats, and mice. These animals can be used as freely moving unanesthetized animal models when telemeters are implanted, and that's a really good starting point. We do not suffer from anesthesia during our measurements. We do not have to restrain our animals. And therefore, some people say that telemetry is the truth. Now, I think that's one step too far, but telemetry is definitely very close to the truth. What do we measure? ECG, very popular. QT prolongation is one of the parameters that is of interest in safety pharmacology. Therefore, we use a electrode position in lead 2, and you can see that on the little picture there. Lead 2 is in fact over the heart axis. So on our animals, it comes from the clavicle and it ends at the left part of the thoracic cavity. If you want to know a bit more about optimal lead placement, have a look at the paper of Andrea Scoifo from 1996 or Marcello Tontodonati from 2011. Another parameter that is important and is very often measured is the blood pressure. And several approaches, surgical approaches, can be used. Classically, the infrarenal abdominal aorta in the rat was used a lot. In the mouse, we prefer to use the left carotid artery, the so-called Butson-Davison technique, published in 2001. In a rat, you can also use the femoral artery, and you can place your transmitter in the abdominal wall, and that also allows you, in the abdominal cavity, sorry, and that also allows you to measure the core temperature of your animal. A few take-home messages for you. First of all, try to refine your surgical technique by using good surgical practice principles. Train under the supervision of experienced instructors and select your instructor carefully. Try to cause minimal trauma to the tissue. And from my personal communication with Bill Russell in the mid-90s, the following list is really very important. Recovery in chronicle models, and we are talking about that when we talk about radiotelemetry systems. Anesthesia, analgesia, perioperative care, the choice of the instruments and the surgical technique should be refined. That was my last slide. Thanks for listening. Holger, the word's to you.
Thank you. I have to start my video back and also share my slides. So yeah, there's one question in the chat, which is called what transmitter placement do you prefer, IP or SC?
Yeah, that's a good question. It depends a bit on what you want to measure. For example, if you need the core temperature of your animal, it's very nice to place it in the abdominal cavity, unless like the telemeters from Stellar, you have a telemeter with a separate temperature probe, and then you can put the body of the transmitter subcutaneous and the temperature probe into the peritoneal cavity. But subcutaneous placement is very, very often used, and especially in the combination of blood pressure and ECG.
Okay, thank you. And is the combination possible between a telemetry implant and catheter technologies, different catheter technologies?
Yeah, you can do that. Of course, it's probably going to be quite a long surgery, more than half an hour to 3/4 of an hour. So you have to have all your things prepared, heating and fluid delivery to your animal, because it can very easily dry out. But yes, you can combine it, for example, with a jugular vein. You can combine it with a femoral vein or a portal vein catheterization, all kinds of ways to sample blood from your freely moving animal.
Okay, thank you. If there are no more questions, I would like to switch, and thank you again for your interesting talk and being with us tonight. And I would like to switch now and hand over the micro to Bob Brockway, which is our global product manager for Stellar, and he's a real expert in telemetry, working since a long period of time in telemetry companies like DSI, and he joined TSE about 2.5, 3 years ago now, and is really an expert, and try to give you now an overview about the big advantage of using telemetry in group house animals. And we all know that this has a very important effect on animal welfare, on the stress level of animals, if you don't need to isolate them. So I'm more than happy to have you here as well, Bob, and thank you very much for giving the next presentation.
All right, thank you, Holger, for the introduction. I'll share my screen now. And there we go. Oh, I have to go back to the beginning. Okay, so thank you for joining us today, and thank you to the Inspire group for allowing us to give this presentation. I want to give you a little bit of insight into the practical use and some of the technology that enables us to do group housing in rodents. A couple of basic slides to start with. Why do we use implantable telemetry? Well, it allows us to monitor freely moving animals under reasonably minimally stressed conditions. It allows for automated collection of long-term continuous data, and it improves the statistical significance of our studies, and in some cases allows us to reduce animal use. Specifically, why would one want to use Stellar implantable telemetry? Stellar gives us the ability to group house animals, and that allows us to further comply with animal regulations and just general best scientific practices. It requires the use of minimal system hardware, a computer, a receiver, and implants. We can provide long-range digital transmission up to several meters, depending on the implant type. We offer implants with onboard memory storage when out of range. We offer solid-state pressure sensors for high-fidelity pressure measurements. The Stellar telemetry easily integrates with other research systems, and it's very cost-effective in terms of the hardware required, the labor, and ultimately the scientific value. So what are some of the challenges of traditional rodent telemetry? Animals typically must be located very close to the receiver or antenna, and often need to be individually housed due to technology limitations. You may need one receiver per animal or per cage. Sometimes there's space considerations. The receivers can be somewhat large. We see increasingly dense housing for IVC cages and space limitations for both animals and for hardware. There's a limited transmission range for dealing with special situations like open field arenas, water mazes, and so on. And that all of this results in the need to design your experiments, in some cases around limitations of the supporting technology. So the Stellar telemetry is a very simple system that requires little hardware. At its core, you need a computer, oftentimes a laptop computer that's portable, one receiver, and one or more antennas, depending on your need for coverage, and then one or more implants. We offer two basic types of implants, what we call memory implants and what we call real-time or continuous implants. On the left, we have a table that compares some of the features. There's a lot of features that these implants have in common. We offer transducer tip solid-state pressure catheters. We can remotely program and control the implants. We can use one receiver for multiple implants or multiple animals. We offer continuous data collection, although the real-time implants are much more optimal as far as battery life and so on. Both also offer scheduled data collection, but the memory type implants are a little more elegant for a scheduled data collection protocol. They both offer fully digital data transmission. Again, with the memory implants, there's built-in memory that provides for remote data collection where necessary. Transmission range of 5 meters or more with the memory. We like to be a little closer with the continuous implants to optimize battery life, so 1 to 3 meters. They're available in a variety of sizes to accommodate a wide range of animal sizes. You can program the sample rates, and the battery life really depends on your use. So whatever you program for sample rates and enabled channels will basically dictate your battery life. So we have these two types of implants. How does one go about choosing the more appropriate implant? This is not a comprehensive list, but it gives you some ideas about why you would use one versus the other. And by the way, the equivalent implant for real-time or memory is the same cost. So you're really just choosing between the modality that works best, and there's no price penalty one way or the other. The memory type implants allow for scheduled data acquisition. Where this is appropriate, they're a good fit for that. They are a great fit for monitoring basic cardiovascular parameters where you're looking for slower trends, changes in things like heart rate and blood pressure. They're ideal for temperature monitoring applications or where you'd like to collect data away from the computer and receiver. They can collect a small to modest amount of data. Real-time visualization is not important, then it's appropriate to store the data in memory for later retrieval. And you'd also use memory type implants if you needed to monitor more than 16 animals simultaneously in a room. The real-time implants are really where they shine is for long-term continuous data collection. If you're doing detailed cardiovascular assessment, for example, doing heart rate variability assessment or arrhythmia assessment, you might need more continuous data. If continuous activity, so locomotor activity is critical, scheduled sampling isn't always the ideal option. EEG applications, sleep, seizure, all require continuous monitoring in most cases. Long-term data collection at high sample rates, real-time visualization, monitoring of up to 16 animals per room. We can do 16 frequencies. Each implant needs its own frequency. And if you need synchronization with video or other telemetry, the real-time implants might be more appropriate. So I'd like to shift gears a little bit and talk about the technologies that enable group housing. And there are several technologies that are implemented in our various implants. First off, digital transmission. By recording and storing the data digitally, we can store the data locally in the implant. We also can provide a digital unique implant ID that allows us to later retrieve the data and match it to the respective animal. The memory in the implant, again, also is important to allow storage for later retrieval. Scheduled sampling allows us to store the data and then retrieve data one at a time from each of the individual implants without restraints on the number of frequencies available and so on. Use of separate radio frequencies, on the other hand, and this is the case with the real-time implants, allows for simultaneous and continuous data collection from multiple implants at the same time. And the use of an ultra low power radio throws in the long-term data collection without needing to recharge and other logistics. So I wanted to show you an example of how the memory implants can be used. On the left, we have an example of scheduled data collection where we're sampling for 15 seconds every 15 minutes. In the bigger graph, every little vertical line is a 15-second sample, and this data was collected over the course of a day, so 24 hours. And we're collecting simulated blood pressure, ECG, temperature, and heart rate. On the right, we're using the same memory type device, but there's actually quite a lot of storage. You can store up to 1.5 days of continuous ECG data, as an example, at a sample rate of 500 hertz. So an awful lot of data. So in this particular case, we've told the implant to store all of that 24 hours of data to memory, and then we download it after the fact. The advantage of this versus recording in real time is that because it's all stored in memory, you capture every single heartbeat. There is not a single point of data lost. That allows for easier data analysis. You don't need to screen out and deal with signal dropouts and things like that. And we'll shift gears and talk a little bit about the real-time telemetry. So there's several considerations in the use of real-time telemetry. We want to optimize the antenna placement. Oftentimes, it's most effective to place very small and inexpensive T antennas local to each cage to minimize interference and to minimize the power required to transmit the data from the implant. We optimize the implant frequencies and locations. So for example, if we're pair housing, we don't put frequency 1 and 2 together. We might use 1 and 3 or 1 and 4 just to minimize the potential for interference. We optimize and minimize the implant transmission power. We can set the actual output power of the implant remotely per implant. We can also set the receiver gain per radio channel. And I'd like to note, higher gain is not always better. And there's a threshold setting in the receivers as well that helps us sort of weed out some of the noise. I want to describe here a little sort of bench experiment that I did in preparation for this, kind of explains some of the considerations. This diagram shows 4 typical rat-sized cages in each corner of a table, a receiver in the middle with 8 inputs. The antennas are shown as the red rectangles. So use my mouse here. So we've got 2 antennas on this cage, 2 on this cage, and then 1 antenna for these other 2 cages. And the implants are shown by green dots. So we have 2 implants per cage representing paired housing. Now on the left here, this is one of the, I would say, pretty cool and useful diagnostic tools that we have in the software. So we're looking at the signal strength as seen by the receiver for all 8 of the channels with 8 implants running in the background. Each of the vertical lines going up to the top of the graph is the implant transmitting a packet of data. And it typically transmits 4 to 10 packets of data a second, depending on sample rates and so on. What we see here is a baseline. So this is kind of the ambient noise and all of those transmissions. And we see from one frequency to another, there's pretty significant differences in how high the baseline is and how wide the baseline is. This is basically environmental influences at these individual frequencies. On the right, we have overnight data collected in the notochord system. We're looking at 1 channel from each of 8 implants. All of these little spikes going down are packets of data that were lost. I want to draw your attention to the 7th one, and we'll compare this to the next slide. So the 7th one has a fair amount of dropout, although still only 0.1%. So we can report the statistics of exactly how much data is lost from within the software. And the corresponding plot is over here. Note a little noise on the baseline and this red line that represents the threshold setting in the receiver. Using this information as feedback, we can make just a couple of minor modifications. We increase the threshold setting. So this red line is raised just a little bit, and we actually reduce the receiver gain. And we see the result here that by reducing the receiver gain, not only did the background ambient radio noise go down quite a lot, but it got a lot cleaner. We don't see these wide bands of interference. And we end up with very, very nice transmission. So looking at the statistics here, the percentage of data that we're missing in one particular implant, the 4th one, we missed 0.04% of data. In the rest of them, we're missing 1 packet, 1 packet, 0 packets, 0 packets, to 14 packets over the course of 13 hours. So with a very simple change based on looking at the original data with no modifications and just a couple of little tweaks, we've greatly improved the environment for our telemetry. So each lab will have a slightly different RF environment. Each radio frequency may have slightly different characteristics and maybe background interference. We provide simple tools and settings to evaluate the environment and the performance of the telemetry and to optimize the system. And again, we can accommodate up to 16 animals per room with very minimal signal loss with the appropriate antenna placement and settings. So now that we've covered group housing, I'll just talk generally about some of the common applications, and I'll try to wrap things up here pretty quickly. Stellar is often used for blood pressure, hypertension, heart rate variability, EEG, sleep surgery, seizure, thermoregulation, metabolism, activity, and left ventricular pressure. On the right, we have some more novel applications: ocular pressure, gastrointestinal EMG and motility, respiration, heart rate in migrating seagulls. So actually record the data in memory and retrieve it later. In the sake of time, I'll move on. We work primarily with 2 software companies, so we do not develop our own software. We collaborate with BioPack and the Acknowledge software, and we also collaborate with Notochord and the HEM software. Both of them do a really nice job of interfacing with the Stellar hardware and collecting data. And here's a couple quick examples of data. This is blood pressure data in rats showing a dose-dependent increase in blood pressure with LNAME on the left, and on the right, a dose-dependent decrease in blood pressure with verapamil. We can use ECG and heart rate variability assessment to assess things like stress and the balance of sympathetic and the parasympathetic nervous system. In this particular case, a stressor was applied for a period of 2 weeks, 2 weeks and 4 weeks, and then we looked at, or this researcher looked at the recovery time and showed that with a 2-week exposure to stress, the animals actually came back to baseline relatively quickly, whereas with a 4-week exposure to stress, they had a much more prolonged impact. And then finally, an example of EEG and EMG for the purpose of sleep assessment in marmosets. We have software tools in the Notochord software to do frequency analysis, bandpass filtering, amplitude of the EEGs and EMGs, and activity is also very helpful to determine whether an animal is active or not. So in summary, Stellar Telemetry improves study results while saving time and money. We offer unique features to accommodate flexible study designs and compliance with regulations. And we facilitate the 3 R's through refinement of the study designs and reduction of animal use. And with that, I will wrap up and see if Holger has any questions to answer.
Thank you very much, Bob. It was a wonderful talk. Thanks a lot. And yes, I received some questions in the Q&A session. So the first one is coming from Anne-Marie, asking the question, after surgery, may the animals be co-housed right away, or do they need to have a period of recovery in isolation before they are co-housed?
Okay. This might actually be a better question for Renee, but I'll offer my opinion. It does partly depend on the animals and the interactions. So for example, if they're pair-housed or co-housed prior to surgery and they're getting along, there's no dominant animals or anything like that, there's a good chance that after surgery, they'll be fine. The main thing is you don't want the animals picking at each other's wounds or causing unnecessary stress shortly after surgery. Personally, if it's allowed and accepted based on your veterinary staff and the regulations, I would choose to house them separately for at least a few days afterwards, and then join them as soon as you reasonably can based on their health and recovery.
Okay, thanks. I hope that helps, Anne-Marie. Another question is, what if I need to perform continuous monitoring on more than 16 animals at the same time?
Okay, so if you want to do truly continuous real-time monitoring, we do need to use separate frequencies since the implants all need to communicate at the same time. And currently we are limited to 16 frequencies. Because the transmission does go at least 2 or 3 meters and sometimes more than that effectively, we really advocate that you limit the continuous telemetry to 16 animals in a given room, or at least have 3 or 4 meters of separation between groups of animals. If, on the other hand, you use the memory type implants, there's really no hard limit to how many implants you can use in a given space or even in a given cage, because we share frequencies and retrieve scheduled data 1 implant at a time.
Okay, thank you. Unfortunately, we are running out of time. I have just one simple last question from the audience, which is coming from Margot Sutter. The question is, if we have implants for zebrafish?
I'm afraid that one's a little tough. All of our implant technology is based on the use of batteries. And, you know, even for our mouse implants, we'd certainly like to be able to offer them in a smaller size. And I believe we will at some point in the future here. Zebrafish is not practical with a technology like ours. I think your best bet would be, you know, something like a microchip that is used for things like just temperature, or in some cases, you can also get heart rate from that type of a system.
Yeah. So as I said, unfortunately, we are running out of time. I would like to mention that we will answer all the questions in a Q&A report, which we'll send to you after the webinar. I would like to thank basically all the speakers and for their nice talks, and would like to finish basically with a small conclusion. And I guess we can all agree on our aim to have optimal anesthesia solution for optimal surgery methods, and that will help us to use stellar telemetry under group house conditions, and this all together will definitely increase animal welfare in the future. And I would really like to thank all of you for attending this webinar, and will give the words back to Peter Jan. Probably he has some conclusion words at the end as well, as the official Inspire project manager.
Thank you, Holger. I really enjoyed the webinar, learned also a few new things. So it was very interesting. I really would like to thank you, but also Irina, Bob, and Renee for giving very nice talks. So I think with this we can conclude the webinar. Maybe I just want to highlight that also next year we will have another webinar on the 27th of January, and that will deal with models of atherosclerosis. So it's the title is Atherosclerosis from Models to Therapeutic Strategies. So also that for those that are interested, you're very welcome to join that webinar. So I think with this we can conclude the session, and I really finally want to thank all the speakers. So thank you and goodbye. Hope to see you later on.